Iacona, and I'll be presenting for Team L1 along with my partner, Jared Zango. So we chose GRAM, which is a paper originally authored in Georgia Tech, and it focuses on graph-based attention models for healthcare representation learning. This paper addresses two challenges, which is data insufficiency in healthcare datasets for rare diseases and also small healthcare ecosystems, as well as lack of interpretability for healthcare models. The objective that we're focusing on that was produced from this paper was using these models to do sequential disease prediction of variable length input and output. We are using the MIMIC3 dataset, selecting a subset of patients that had 2 or more visits. And we're going to be surveying the following models: the RNN plus, the GRAM plus models. The plus stands for the inclusion of an initial embedding vector given by the GLOVE algorithm, the Global Vector Representation Algorithm. The hypothesis we're going to be focusing on is representing ontological concepts hierarchically through an attention mechanism will increase accuracy in modeling tasks, such as the previous objective, the one we're focusing on, which is sequential disease prediction. In future work, we are open to considering as well how the hierarchical representation increases interpretability from qualitative model evaluation as presented in the original paper. Our baseline model is the RNN model, and it has 2 steps: data preparation and predictive modeling. So first, in the data preparation, we prepare a list of codes that go into a list of visits, that go into a list of patients, producing the entire input matrix, which is then batched and passed on to the predictive model. For the input layer, once that data is received, it passes through then an embedding layer, which changes the dimensionality and assigns weights to each one of the embedding columns. Then it goes through an activation function, which in this case is a hyperbolic tangent function. It goes through a GRU, which is a gated recurrent unit with hidden states and gates, controlling how previous data is considered for current predictions. It goes through a dropout layer, which allows us to make a more robust model. Once it's been dropped out, then it goes through a linear layer, which allows us to scale it down to the output number of classes. And the activation function is right before that output layer, and it's going to help us prepare that data for the output classification. So the biggest difference between the baseline model and GRAM is actually in the embedding layer, which incorporates an attention function. This attention function has 3 components. First, an ancestry graph which creates a hierarchical representation of diagnostics codes, as well as the attention weights for each one of those ancestor codes, as well as the leaf codes. And then it has a third last step, which you must stay tuned for, as it's very important. That's the only difference. So for the first part, we're going to build a ancestry graph for each one of the concepts. Here on the left, we have a tree where a diagnostic code, as it gets more complex, it goes down the leaf nodes. And the really interesting thing about this is as patients go deeper down into this graph, the diseases and these codes become more rare. So as seen on the right, we can augment those rare codes or less occurring codes with the ancestor codes that allow us to better address the similarity between these diseases. For each one of these concepts, we want to generate a weight that's going to allow us to understand when we're actually outputting a representation of this, a visit representation that addresses the importance of each one of these nodes within the hierarchy. So that's represented here on the left side. And the attention layer is actually these weights that produce a final embedding, which is then used in tangent with the list of codes within the visit to produce a visit representation and allow us to get better prediction accuracy. The hyperparameter search space for both models is going to be the input embedding size, the hidden layer size for the RNN, the L2 regularization rate, and the dropout rate. An additional parameter we will be searching for in the GRAM model is the hidden layer size within the attention generation algorithm. So once we see the RNN and the gram results, this is steady state end of training result. We see really similar test AUC, but we see a huge difference in the initial 30 epochs, where we see a giant inflection, very quick learning on terms of gram. The only difference between these models is the attention layer. So in the stay tuned step, we initialize the embeddings for model training with the global vector representation algorithm. For the RNN, we use the final diagnostic code seen in the visit. For the gram model, we actually augment these with all the ancestor codes for those diagnostic codes within the visit. Then this creates a global co-occurrence matrix, which the glove algorithm uses to figure out an embedding matrix, which best represents the reconstruction of this global co-occurrence. For both of the models, we see the test AUC dropping out to 93% steady state at the end of the training. But we see a huge difference in the early training stage for both algorithms, where the gram plus is very quickly able to jump through AUCs, and the RNN has a more linear learning curve. Overall, if we look at the results with the different epochs in the early stages, we see a huge improvement in terms of percent change between the AUC scores observed on the test data for RNN, RNN plus, gram, and gram plus, with gram plus being the significantly best algorithm. Some notable findings is that early stage learning is vastly accelerated by initializing the embeddings with GLOVE, also by adding an attention layer. Another notable finding is that at the late stage, at the end of training, the models top out at 93% AUC on the test data set. This leads to us thinking that maybe it's limited by the information available in the data set provided. Maybe it didn't reduce enough entropy. So given more time, we would be able to analyze and compare the interpretability of these models using a TSNE scatter plot as the original authors did. We would also consider different subsets of patients, maybe more focusing on rare diseases and comparing the performance on early stage or scarce data. We would also explore the hyperparameter space more granularly by exploring it through smaller chunks. Also, we would apply the attention layer to other modeling tasks, such as heart failure prediction, as the original authors did on the Sutter Health dataset. For our references, we have Edward Choi and his co-authors on the Graham paper, as well as the providers of the MIMIC3 clinical dataset. Thank you.